Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. Today in this video we are going to see the derivation of a method. So the second method that we are learning is called slope deflection method. So let me just write it down. It's generally called slope deflection method. Slope deflection method is based on displacement. Okay, it's very much different from force method, where force method is force based, but slope deflection method is displacement based. I think I will explain it further in class. So today what we are going to do instead is to do a little bit of derivation, because slope deflection method will require you to use a few equations in order to solve your problem. Okay, so right now let's see how the equations are derived. So say we have a continuous beam. Okay, the continuous beam means that it could be very long. Okay, so say we have a beam that is few span long, and then you have some arbitrary load. It can be of any type of loading. Okay, and imagine also that on top of the loading, your support also displaced down. So this support also goes down here, and this support also goes down here. Imagine so what happened is you are going to get a beam that exaggerated, that will deform in that direction. Okay, so I can call this as my relative displacement. Okay, and then let's call this point as point A and the other point as point B. Okay, so if I look at only span AB, okay, this point A and point B will have relative displacement. So let's call this relative displacement as delta AB. Okay, meaning the relative displacement between point A and point B. And then imagine also that this beam also have rotation. Okay, so let's call this rotation as theta A, and another rotation here which is theta B. Okay, all are clockwise, and then on top of that it also has this load. Alright, so imagine that you have this type of problem. So what we are going to do now is that we are going to draw the free body diagram of this problem under the given displacement and also rotation and also load. Okay, so let me just push it upwards. Okay, so imagine that your beam looks something like this. Right, and then you have some arbitrary load on it. Okay, the load doesn't matter. It's W, and then you have point load also P, and then with that you have the displacement delta AB, rotation theta A, and rotation theta B. Sorry. Okay, so I've mistakenly deleted that. Okay, so with this then, imagine that your beam is actually continuous, and so we can somewhat idealize it as fixed. It's not really fixed, okay, but it's continuous, so there will be moments at point A and point B. So let's call this moment at point A. Okay, it's clockwise. Assume it to be clockwise, because in this method all clockwise rotation is positive. Clockwise rotation and clockwise moment. Rotation and moment, we are considering them as positive. So if you look at this problem, then at point A you are going to develop internal moment. So let's call this internal moment as MAB, means the moment that is developed at point A, okay, within the span AB. Okay, this is A and this is P. So the span is span AB, but this is moment that is nearer to point A. And then the moment that is going to develop here, let's assume it to be clockwise also. And this moment is M BA. Okay, span the same span AB, but the one that is nearer to this moment is actually point B. Okay, so if you see this problem, then now it will look a little bit messy, sorry, but in essence, the moment that is developed is basically a function of the load that you apply, the rotation. Okay, so for moment AB, then, okay, is a function, this moment happens due to the load, due to rotation A, due to rotation B, and also due to displacement. Okay, what this is trying to tell you is that the moment that happens here, okay, occurs due to all these factors combined. Okay, load, rotation A, rotation B, and displacement combined. Okay, so if you can discretize them, okay, divide them into different sections and superposition them, okay, you will get back the original. Okay, so say I discretize them due to each effect one by one. Okay, so what is going to happen is that this system, okay, first of all, I just take the effect of loading only. Sorry, it's supposed to be straight. Okay, let's see, straight. Okay, let's take first the effect of load. This is W plus a point load. Okay, this is only due to load, plus, okay, the effect only due to rotation. So what I'm going to do is point A here, I'm going to rotate it by delta A. So let's give point A a rotation. Okay, so this is the deflection. The rotation is clockwise. Okay, but then you hold joint B constant, no rotation. For this case, then the deflected shape is going to look something like this, right? There's no rotation at the ends, but then it will go down due to the load. Okay, then this one, okay, also due to only displacement at B. You just put the displacement at B. So you force this to rotate clockwise, so it's going to look something like this. Force it to rotate. Okay, so this is theta B. And then due to only displacement, so what we are going to do is we are going to apply only displacement. Okay, force it to go down, or better still, this is the original beam, it's straight. Now you force it down by delta AB. Okay, so this is the new beam. Alright, so then if you look at this problem, right, what we are going to do is we are going to get all of the moments. Okay, for example, this moment, this is moment at A due to load. Okay, usually it's cofixed and moment. This is the moment at A due to rotation. This is the moment at A due to this rotation A. This is due to rotation B, and then this will be the moment that is developed due to displacement. Okay, so what we are going to do is we are going to develop the equation to describe MAB, which will be equal to MA load plus MA theta A plus, so this is actually a notation, okay, plus the moment at A due to theta B plus moment at A due to the displacement. So we are going to get what each individual values are and then add them together to get the actual moment. Okay, so now in order to get each of the individual moment due to each effects, what we are going to do is we are going to use the method that we know already how to, which is called our force method. Alright, so let's use our force method. Okay. Alright, so for force method, if you can still remember, okay, if this is your structure, okay, you just have rotation and nothing else, no load, no nothing. Okay, this is your rotation, theta A. Alright, your objective is to find the moment that is developed at each end. So let's call this as MAB. We want to call it prime, sure, MAB prime, and then this is MBA prime. Okay, so these moments are developed only due to rotation. So how many degree of we have to decide how many degree of indeterminacy. So the static indeterminacy cantilever is 3, so you add another fix, it will become 3 degree of indeterminacy. Okay, however, for beams, okay, usually we can neglect the actual restraint. Okay, simply because beam are considered as structural member, so we ignore the actual restraint. Okay, we only need one actual restraint to make it to satisfy the equilibrium equation. Okay, the other one we can ignore because another assumption is small deformation assumption, so it should be okay. So then you are left with only 2 degree of indeterminacy if you ignore the actual restraint in the other support. Okay, so if you remember force method, what we are going to do is we are going to use superposition. Okay, first, okay, this is our actual system. Let's use green color. So this is called our actual system. Okay, it will be equal to the primary system. So let's choose this n, not a good color. So let's choose this n as your redundant n. Okay, so what we are going to do is we are going to have our primary system. Let's call this as primary. If you remember, primary system only have load on it, so there's no load, so primary system is just like this. Last primary system is system 0 plus the first redundant system. Okay, let's take the first redundant as your reaction at A, the unit load, and then if you still recall, you have to multiply the whole system by RE. Okay, it's the reaction at A here. Okay, you will get displacement, so let's call this displacement as delta 1, 1. The displacement at 1 due to the redundant system 1. Okay, and then you also have rotation that you remove, so you need to measure that rotation also. Okay, so this is the rotation theta, sorry, alpha, let's call it as so for similarity reason, let's just call it as alpha to 1. Okay, the rotation at the second point, okay, which is second point is basically the rotation due to redundant system 1, plus, okay, now you apply the moment only. Okay, so you only apply a clockwise moment. Why clockwise? Because we want it to be positive clockwise. Okay, so you will get the structure that deforms like this. Multiply the whole system by moment AB prime. Okay, so it's going to move up. Oh, sorry. So it's going to move up. The displacement is delta. Now it's called delta 1, but system redundant 2, and the rotation is alpha 2, 2. Okay, due to redundant system number 2. Okay, again, it's the why do we have so many systems is because we assume it to be 2 degree of indeterminacy. So we have primary system plus another 2. Okay, so then what we do is we write down the compatibility equation. Okay, if you can still recall, compatibility equation is you write down the equation of the displacement condition. So the first displacement is delta, because you have reaction, so delta A, let's call it as delta A. Okay, this is equal to delta A is the actual system, equals to the primary system, which is delta 1 plus, okay, delta 11 RA plus delta 12 MAB prime. Okay, you are taking the condition of displacement for each of the same displacement point. Okay, and then we also know that the rotation at A should be equal to, rotation at A is here for the actual system, should be equal to the rotation, let's call it as system 2, okay, point 2, even though it's the same point, but it's actually talking about the second condition. Okay, theta 2 plus alpha 21 RA plus alpha 22 MAB prime. Okay, so you can also write it down in matrix format lah. So matrix format, you will get what, delta A, theta A equals to delta 1, delta 2 plus delta 11, delta 12, alpha 21, alpha 22 multiplied by RA and MAB prime. Okay, so just to make our life easier, so just change this alpha to displacement. It will make our life easier, just because it will avoid confusion. Okay. Alright, so then with that, then in order for you to get what's the values inside this parenthesis, what we need is, if you can still recall our last few classes, okay, basically delta ij is equals to the integration of mi mj divided by ei dx. Right, so what you need to do is just to find out what's the moment. Okay, so for example, for the primary system, if you want to cut it, you cut it from the left to the right, yeah? But you only need to cut once because your load changes once. Yeah? Okay, so this is load and displacement. Okay, only look at the left side, don't look at the right side. We are taking from the left to the right. Okay, so for the primary system, there's no load, so basically it's 0. So this one, delta 1 and delta 2, we know it as 0 because we don't have any load. Alright, so in order to get what's all the others, you have to find the moment. So for system integrator number 1, okay, this will be your shear and this is being moment. So M1, ignore the right part. Similar to system number 2, which is shear, this is moment, ignore the right part. Okay. Alright, with that then, what you are going to get is basically M1 is going to be equal to this is x1, right? So you are going to get 1x1, okay, and then if you calculate what's moment 2, it's going to be just 1, right? So then if you integrate them, if you want delta 1, you are going to have from 0 to L M1 divided by ei dx. Okay, so if you put 1 here to integrate them, you will get x1 squared over EI dx1. So basically you are going to get L cubed divided by 3EI. Okay, because your limit is 0 to L. Okay, so now to continue and try to find what's the displacement 1, 2, which is actually equal to displacement to 1, 0 to L, m1, m2 over EI dx. Okay, so you get limit of 0 to L, so x1 times 1 over EI dx. Okay, it doesn't matter x1 ke x2 lah basically. Alright, so with this, solving this, then you are going to get the answer of L squared over 2EI. Okay, and then finally for 2, 2, you are going to get m2. Okay, so 1 squared. Okay, finally it will be L over EI. Alright, and then putting it all in the matrix. So basically you are going to put all of this back here. Okay, so you already know that the displacement at A is 0. Displacement at A is basically 0 because point A here is not moving. Okay, so then this equation will result to, I rewrite it down, 0 theta A equals to delta 1, 1. I can also take out the EI. So 1 over EI. So delta 1, 1 is this one. L cubed over 3. Right. Delta 1, 2 is L squared over 2, which is the same here. And finally it's L. Okay, and then multiply by RE and MAB prime. So solving this, yeah, all of this, you will get MAB prime equals to 4EI over L. Okay, hopefully you can solve it. And then with that you will get RA equals to negative 6 over L squared EI theta A. So what this means is that under the system, this original system here, okay, we already got MAB and RA, and then you can find MBA. So this is particularly using only equilibrium. Okay, so okay, if under the applied rotation, okay, you will actually get MAB, which is 4EI over L theta A, and then you get reaction 6 over L squared EI theta A. It's negative, so it's going down because our assumption is the displacement is going up. Okay, so then in order to get what's your MBA prime, so it's basically MBA prime, you use equilibrium, so it's basically RA times L. Okay, again shortcut way, RA is producing a counterclockwise moment that is opposite of this one. Okay, but then minus because this moment is the same direction as this moment, so it's going to be minus MAB prime. Sorry, I should not do this here. It's going to be equal to 6EI theta. This is easier, over L squared times the length. Okay, this is RA times L. and then minus because same direction 4ei over L theta A. Okay, solving this you'll get 2ei over L theta A. So if you notice, what happened is, if you have an applied rotation at this point A, okay, the moment that is going to develop at point A is going to be 4ei over L. The one that is going to develop at the opposite direction is only 2ei over L theta A. So simply put, half of the moment gets transferred to the other end. Okay. Alright, so then you can repeat the same procedure for all of the other cases. Alright, so I actually drew this. Okay, so if you are considering, look at the first part here, okay, only rotation at B. So if you still remember, okay, first only due to rotation at A, so we've solved this. Okay, so and then we are going to look at the others. So second case is only rotation at B. So if only rotation at B, it's the same as before, just opposite, kan? So the one that is nearer to B, if you apply a rotation that is clockwise at B, the one that is nearer will develop 4ei over L. The one that is further, you are going to develop half of it, so 2ei over L, theta B, because it is due to rotation at B. Right? Okay, further, if you consider only displacement or settlement in this case at AB here, okay, you are going to develop two moments, MAB and MBA. So using force method again, okay, so basically the this is actual. Okay, your primary structure, as you noticed before, because you don't have load, it's 0, nothing. Okay, then plus the redundant 1 system and then redundant 2 system. Okay, so basically redundant 1 is a unit load and redundant is the applied moment. Okay, so in essence this is quite similar to the one before. Okay, so if it's similar, what's happening, if you can still recall what I teach you the other day, if it's similar, then the constant in this parenthesis will be the same, having the same value. Okay, the only difference would be this part, which is the actual displacement and actual rotation. So for the actual system, okay, there is displacement, but rotation at B is equal to 0. So that is why the equation looks like this. Alright, so this is known, and you can take the value as similar to the one that we have developed before. So if you put it inside MB, if you solve this, you will get MBA as this, RB as this, and MB as this. So basically, okay, if you look at these results, okay, if you have displacement, okay, at the other end like this, okay, so this is delta, the displacement. The moment that you are going to develop is basically a counterclockwise moment. It's negative, kan? So counterclockwise moment, and the value is 6ei over L squared delta, and also 6ei over L squared delta. Okay, these are the results. Okay, and then finally, for the last part, so we've developed for this one and this one, and then for the last part, which is due to the load, okay, the moment that is developed is basically, you can also derive it from force method, but basically, usually they are given. So these moments that are developed due to the load, we call it as fixed end moment, FEM. Okay, FEM is simply fixed end moment. They are the moments that are developed within the member, okay, due to only the load applied and the two other ends are fixed. Okay, so fortunately for the fixed end moment, they are available in many tables, in many books. I even gave you one copy at the back, okay, of the leaflet that I the handout that I gave you in class. So it's basically, usually they come in a table like this. with predetermined load. Look here, and there will be predetermined, and this would, the moments at the ends are all fixed and moments values. Okay, look here, when you have point load, PL over 8 is at 2 ends. When you have uniformly distributed load, there will be WL squared over 12 that is divided at 2 ends. So it's basically the moment that is resisting the deformation. So if you have a point load here, so the whole thing is going to be shifted downwards, right? So the moment that is resisting, okay, will be these two moments, right? And these are all coefficient moments. So this will be given to you. Alright, so again, this is our original system. Okay, so based on the moments that we calculated, okay, these are the moments due to each effects one by one. Alright, so if you want to find what's MAB, what you do is you add superposition. Using superposition principle, you just add each of the effects one by one. Okay, so you will get 4EI over L theta A plus 2EI over L theta B. Okay, all of this I got from force method. So minus 6EI over L squared delta. Okay, and then plus fixed and moment at AB. Alright, and then if I try to simplify them, what I do is I take out 2EI over L. Okay, I will get 2 theta A plus theta B minus 3 over L delta. Okay, and then close parentheses, and then plus. Usually the sign in textbook is plus minus fixed and moment AB, because the fixed and moment can be positive or negative depending on where it is. Okay, so usually you use the sign of plus minus, and this is actually the general equation for slope deflection, and this is the equation that we are trying to develop just now. Okay, so if you look carefully, okay, when we are talking about the moment at near NA, okay, the joint that is nearer is joint A, you will see that in this equation, okay, it will be 2 theta A and only 1 theta B. Okay, similarly, you can repeat the same procedure and calculate MBA. Okay, MBA would then be, the MBA is here, it would be equal to all these add them together. Okay, so if I do the same thing, I take out 2EI over, so let's not do that. Let's write down the general equation first. It's 2EI over L theta A, okay, this one, okay, plus 4EI over L theta B, okay, minus, okay, because it's a negative sign, 6EI over L squared delta, okay, and then plus minus, fixed and moment BA. Alright, and then if I simplify, then MBA is going to be 3I over L, take it outside, theta A plus, this one, sorry, this is not theta A. Okay, you look here, it's actually theta B kan, typo, sorry ya. Okay, so it's going to be 2 theta B, okay, minus 3 over L delta plus minus fixed and moment BA. And this is the slope deflection equation for BA. Okay, you have AB and BA. So notice that the main difference depending on where your starting node is. If your starting node is A, then theta A would have 2 times bigger, okay, compared to theta B. And the other difference is the fixed and moment. Okay, and then if you have BA, the nearer node is the B, okay, then the one that is 2 times larger is theta B. Okay, but other than that, they are all the same except this fixed and moment BA. Alright, sometimes in some books they also simplify delta over L, okay, this term, as equal to psi value. So it's going to be blah 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 minus 3 psi. Okay, again, it's the same thing. So it doesn't matter which notation that you use. It's actually coming from this principle. Alright.